So we can now say, let's take two planets or two stars, two objects in space, and then say, what kind of questions can we ask about that scenario, okay, about that situation. So we can say a star of mass 3 times 10 to the 30 kilogram, we call it star A, and star B, oh, let's see here, is at negative 10 AU, and well, star B of mass 5 times 10 to the 30 kilogram is at 30 AU. Okay, so star A of mass 3 times 10 to the 30. So remember on Monday when we covered the masses of our sun and planets, we saw that the mass of the sun was 2 times 10 to the 30 kilogram, and then we gave a range of different masses. We said this is the heaviest that a star can be, this is the lightest that a star can be. So this star A is slightly heavier than our sun then, and it's the same order of magnitude, and it's at negative 10 AU. And star B is heavier than the sun also, 5 times 10 to the 30, and it's at 30 AU. So the distance between them is 4 AU. So this would be a classical system of a binary star system, which is, they're pretty close. Some binary stars can be 50 AU away from each other, some can be 100 AU. This would be 4 AU. So this one would be really hard binary star system to tell apart because they're so close. Your eye sees them as a single star, right? But a lot of these kind of binary star systems do exist. And then 1 AU is called the astronomical unit. It's 1.5 times 10 to the 11th meters, which is known as the average distance between the Earth and the Sun. Okay, so then we can ask, what is the force of attraction between the two stars? So that's one question we can ask, a basic one. What is the force of attraction between the two stars? B, we can say, where along the line joining the stars is the force of gravity or joining the stars is the force of gravity on a third star equal to 0. So where along the line joining the stars is the force of gravity on the third star equal to 0. C, we can say where along the line joining the stars is the acceleration of gravity equal to 9.8 meters per second squared. So what is the force that the two stars exert on a third star placed at the location given by the answer to C? And then E, what is the force that the two stars exert on a third star placed at the location? You could say 4 AUs. So these are a variety of kind of questions we can say, given this scenario. So we have two stars. -1. So mentioned here, this is star A, and then the other one is at 3 AU. 1, 2, 3. This is star B. This one is 3, 0 AU, -1, 0 AU. Okay, so the force of attraction between the two stars is going to be Gm1 m2 over r squared. So 6.674 times 10 to the minus 11. 2 times 10 to the 30th. 5 times, or no, 3 times 10 to the 30th. 5 times 10 to the 30th over their distance, which is 4 AU, right? 4 AU. But then each AU is 1.5 times 10 to the 11th. And then we'll square that. So then put all of that into the calculator. .781 times 10 to the 27th. Is that it? Okay, questions? See how I got the 4 AU? The distance between them is 4 AU, but then each AU is these many meters, then you're going to square that. These two, you're multiplying the masses, you're multiplying by the constant of gravity. So B, where along the line joining the stars is the force of gravity on the third star? So there's a location here where if you put a third star there, you would experience no force. You would be attracted by the two stars equally, right? Where can that be? Can it be somewhere in the middle?
Yeah.
We can call this one region 1. Region 1, yeah, probably if it's, since this guy is the heavier one, right, this is 5 times 10 to the 30th, this one is 3 times 10 to the 30th. So probably if I put it a little bit closer, right, a little bit closer to this guy's going to attract it, and then that one is going to attract it. So we can say some random location x0, right? But I could also put it on the opposite side, closer to this guy. Well, it's going to naturally be closer to this guy, right? So somewhere here, and then this guy's going to, oh no,
That's not possible.
because then they're both going to attract it.
Yeah.
and the two are gonna just add up. So actually it can only be in the middle region, right? It can't be here either. So if you put it anywhere here outside or here outside, the force of attraction, they're both gonna be attracting that object, right?
Yeah, because they're positive, not like coulomb.
Then they add up.
Yeah.
The other way to ask this question is to say where along the line joining the stars is the acceleration of gravity. The acceleration of gravity 0 meters per second squared, right, which is the gravitational field. So if the gravitational field there is 0 meters per second squared, that means you can just put an object and it will just float. That's true weightlessness. We call that spot. That spot becomes a spot where you're truly weightless, right? Unlike the weightlessness of the astronauts in the spaceship, we call the astronauts weightless, but they're not really weightless. The astronauts in the spaceship, they actually have weight, but it's just that they're floating in the spacecraft because they're going around the sun, the Earth, right? So they're not truly weightless. But if you're at that location, you are truly weightless. You have no weight at all. Okay, so then we're gonna say the force on the third object. This is the third object. The force on the third object due to star A, the magnitude of that has to equal the force on the third object due to star B. So then G mass of star 3, mass of star A, over x minus 1 squared is equal to G mass of star 3, mass of star B, over x minus 3 squared. So if you're at a location x, your distance from here is going to be x minus -1. And then this is the mass of star 3, which whatever the mass that you place there. And then this is mass of star A. So that's the force of gravity between the two. So then this is F on 3A. And then this one is F on 3 due to star B. Right? And that's going to be mass of star 3, mass of star B over this. Well, then what's going to happen is the G doesn't matter in this problem. The G cancels. Mass of star 3 also cancels. That means you could put any object there and it will be weightless, right? As long as the acceleration due to gravity is 0, then a rocket placed there, the Earth placed there, a human placed there, they will all experience no weight. So then now here you have the mass of star A, which is going to be 3 times 10 to the 30th. And then here you're going to have 5 times 10 to the 30th. X minus 3 squared. And then the 10 to the 30th will cancel too. So you literally have 3 times x minus 3 squared is equal to 5 times x plus 1 squared. Now you can put this into solver. On your TI, go to, if you have the TI-89 titanium, go to F2, algebra, and then the first option is to solve. And then you can put that equation as is. 3 times parentheses x minus 3 squared equals 5 times parentheses x plus 1 squared, comma x. And it spits out both answers to you immediately. So you've got negative 14.74. So what it's going to give you one answer that's here, because it's going to say if you place it there, the force of gravity is the same at that location. But we know they don't cancel because they're in the same direction, you see. So we're not going to accept that answer. The only answer we're going to accept is in between the two. So the other answer is the one that I'm looking for. 0.746. .746. Now what units is this in? Notice when I solved it, I didn't do it in meters. I just kept it in AU, right? I didn't worry about converting to meters. So the answer here that I'm gonna get is in units of AU. So essentially, it's gonna be somewhere here. Yeah, actually, that's exactly where I had drawn, you know. It's a little bit less than 1 AU, and it's closer to this guy than it is to that guy. So if you place it there, you are truly weightless. So any object placed here is truly weightless. Okay, then we have question C, where along the line joining the stars is the acceleration of gravity 9.8. So, in other words, I want to know where can I place my object so that that object will feel the same gravity as it does on the surface of the Earth. So I place a human there, right? Because if I place a human here, he's going to feel weightless. But I want to know where can I place the human so that he will feel the same weight that he does on Earth. You see. So then, what do I want to do? Well, there might be a couple different places where the gravity is 9.8. Maybe somewhere, because if I keep getting closer to here, what's going to happen? Then the gravity of this is going to win over the gravity of that. The gravitational field is increasing as I go this way, right? Because remember, over here it's 0. So over here, as I go this way, the gravitational field is increasing. So I expect there to be somewhere here and somewhere here, where it's 9.8. Then over here somewhere, there might be a place where it's 9.8.
So
Over here, there might be a place where it's 9.8. So I think there should be 4 answers, probably. Because as you keep going further away, it's going to approach 0. So we know at infinity, the gravitational field is 0. We know over here somewhere, the gravitational field is very strong. So just by reason of continuity, you can say it's a continuous function. So there should be a place where it reaches 9.8. There should be a place where it reaches 9.8 here. And then here, there should be 2 answers. So then in region 1, how do I set this up? In region 1, the gravitational field is going to be what? It's going to be the difference of the gravitational field due to one and the other, right?
Right.
Because they're competing against each other.
Yeah.
So then you have here G mass of star A over X minus -1 squared minus G mass of star B over X minus 3 squared. And that's equal to 9.8. And so you have here G is going to be 6.67. 4 times 10 to the minus 11. And then mass of star A, 5 times 10 to the, or is that 3? 3 times 10 to the 30th. Right? And then you're going to have here 6.674 times the 10 to the 11th. That's going to be 10 to the 19th. So actually, I can factor that out. 6.674, 10 to the 19th, right? And then I have 3 over x plus 1 squared minus 5 over x minus 3 squared. That's equal to 9.8. Right? Because this 10 to the 30, 10 to the minus 11, that's 10 to the 19th, and then there's another 10 to the 19th there, so that factors out. Then the 6.674 factors out. Then you just have the 3 over this minus this over this, that's equal to 9.8. However, I do need to account for the fact that these are AUs now, right? Because this is equal to 9.8 meters per second squared. In order for it to be meters per second squared, I need to change this to AU. Here I didn't worry about it because I was just setting them equal to each other. In essence, I was just saying this minus this equals 0, right? And so I didn't worry to change this to meters, because if it's 0, then it doesn't matter the conversion. Here it's equal to 9.8, so then I need to account for that. So how would I account for that? Well, I would say 1 AU is 1.5 times 10 to the 11th, and then that's squared. So that can factor out. So then literally I have 1.5 squared factors out, and then 10 to the 11th squared factors out, which becomes 10 to the 22. You see? So I'm taking this portion, and I'm saying I'm going to factor that out. Yeah.
Yeah, I don't know if you should put an absolute value for the difference right there, because I estimate there might be two. I mean, in region 1 there might be two locations.
Yes, yeah, because when you go over here, this is going to be this minus this.
That's right. So that's why you put an absolute value.
So this minus this equals 9.8, but then once you're over here, this is going to be greater, this minus this. Yeah. So I'll probably have to flip them then, right?
You just put an absolute value. And
yes,
you can
exactly.
solve that.
On the calculator, I don't know, I'm not sure if you could put the actual value.
I'm not sure too.
Yeah. Okay, so I think that's it as far as, so the only simplification you can do is 6.674 over 2.25. This is 10 to the minus 3. Equals 9.8. Okay, now let's put that in solver. With the TI-89, this is where the advantage is coming, because as soon as we put an equation in, it gives us all possible solutions to that without us having to search one by one. With the 83 and the 84, you're searching usually one by one to find out what the possible answers could be. So then we go to F2 algebra, solve. Okay, we have 6.674 divided by 2.25 times 10 to the power negative 3 times parentheses 3 divided by x plus 1 squared minus divided by x minus 3 squared is equal to 9.8. Let's see here. Negative 1.03, and then these will be in units of AUs. Negative 1.03 AU, so it's over here. But that one we cannot accept as a solution.
Right.
Yeah, because it doesn't fit our equation. So that's basically, you just dump that solution out.
Should be fine.
So I'm going to write it down just so that you can see the solutions that it gave me. Negative 1.03, or the other answer is negative 0.96986 AU. Just two solutions. And of course, the only one I'm going to accept is this one, which is perfect. So that's interesting. You have to really get close to this star. That's really close, 0.96986. So very, very close. Of course, I drew the star too big, It's not that big. The star is something like this. And so you probably have to get here in order to feel the same gravity. So you're not really touching the surface yet, you know. You're probably boiling at that point. You're so hot. So yeah, at that point you feel the same as the gravity of the Earth. Okay, now to get this answer here, we switch the order of the minus. You see? So then you just say, you switch this, or you could just put a minus here. Either one. Okay? So you go back to the equation, and you make your necessary correction to the equation. So now you're going back in here. I'm going to put negative 9.8. So now it's also probably going to give you two solutions. 2.961 AU. So then switch the order, and then these are the answers it's giving me. 2.961 AU, which I'm going to accept that. So then that's like right here. So now this star wins, right? Or the other solution it's giving me is 3.0389, and I'm going to dump that answer. So only keep this answer, 2.961 AU. Okay, so then that one takes care of this spot, that spot. Okay, now we do over here.